So in order to help understand a little bit more the regression coefficients in the multiple regression setting, let's look at the regression coefficients that we estimate with the data on California school districts. Recall we have 420 school districts. We have two explanatory variables, the student-teacher ratio and the percent of English language learners. And if we estimate that equation, we get our estimate for the intercept, our estimate for the first coefficient, and our estimate for the second coefficient. So we have test scores is equal to 686 minus 1.1, student-teacher ratio minus 0.65 times the percent English language learners. So that's these are our estimated regression coefficient. Now we can interpret this, right, by thinking about first what's the residual for any given person. So we have minus 1.1 times the student-teacher ratio, and then minus 0.65 times, I'll just call it E, the percent English language, or call it EL, percent English language learners. So suppose we have a school district that has student-teacher ratio of 20. So we imagine or look in our data and see if there is one. And we have another school district, and the same school district has English language learners of maybe 50%. So our predicted test score, our predicted test score for that observation or a prediction for a hypothetical school district would be 686 minus 1.1 times 20 minus 0.65 times 50. All right, so that's our 20 here and our 50 here. So now we just go and do the math. We have 686. 20 times 1.1 is 22, so minus 22. And then 0.65 times 5 is 0.30, 0.325, I think. So it's 32.5. I could be wrong on the math, I'm just doing it in my head. So we have 686 minus 54.5, so that's 631.5. I think, again, I'm just doing it in my head, right? That's our predicted test score for that school. Now notice before we could easily graph the student-teacher ratio and the test score, and we had our line and we had points here, and we could see what the residual, the UI hat was. Now we have two explanatory variables, and so it's 686 minus 1.1 student-teacher ratio, minus 0.65 English language learners, right? So we can't draw this anymore in two dimensions. So that's why there is no equivalent graph. We'd have to draw a three-dimensional graph, which is always hard on two dimensions, right? You end up with three axes like this and trying to make it, and then the points are floating here in the air. In this three-dimensional graph that you're representing in two dimensions. So I've always thought that's kind of a bad idea, and so I'm not going to draw graphs like that, right? So instead we have to think of the analogy from this one to this. So for every observation, we can calculate the student-teacher. If we knew what the observation student-teacher ratio was, their English language learners were, and we knew what their test score was, then we could calculate the residual, the UI hat, for that particular observation. So again, remember, we compute the beta 0 hat, beta 1 hat, and beta 2 hat by choosing values for these to minimize the sum of squared residuals, and the sum of squared residuals is just the sum of the UI hats squared, right? So that's the sum I going equals 1 to n, so that's the same as the difference between, in this case, it would be the difference between test score and beta 0 hat minus beta 1 hat for the student-teacher ratio minus beta 2 hat for the English language percent and all that squared. So that's, these two are equivalent, right? They're the sum of squared residuals. That's, I think, about it for interpreting these coefficients and thinking about these coefficients.